Okay, so this is active filter design, lecture 37. So far in this course, we have seen how to come up with approximations, how to derive a transfer function based on the approximation, how to synthesize an LC network which realizes the transfer function, how to realize an active network using transconductors and capacitors, which also emulate the LC ladder network, or on the other hand use a cascade of biquads to realize the same transfer function. Then we have seen how we can make these transconductors fully differential so as to give good immunity to common mode noise sources, right. So then we have seen common mode feedback, all the stuff that goes into making a fully differential circuit work. Then we realize that the time constants or the bandwidth of the filter depends on factors of the form Gm by C, which can vary with the process and with temperature. So we have seen various ways in which one can stabilize Gm by C, right. One way is to simply servo Gm to a fixed resistance which is outside the chip and does not change with process and temperature. Another way is to use some kind of loop to determine the time constant, compare it against a known time / frequency standard, and use negative feedback to tweak the bandwidth to get to whatever you want, right. So with all this, we now have, in principle at least, accumulated the knowledge of how to build a filter completely from scratch to finish, right. So let us say you have gone through all these steps and then you finally built the filter. The next job is to actually send it out for fabrication and the chip comes back after it is fabbed, and the next job is to do what? Test the filter, make sure that you actually get the response that you designed for, right. So in this talk I will focus on filter testing. As I indicated to you at the beginning of the course, most of the time these filters are required only as the front end of a large system which is on chip. In other words, perhaps you have the input, this is a big analog system, you have the input which perhaps needs to be amplified, right, and then you have the filter, and then you have the A to D, and then this goes to DSP and so on. So this is the block diagram of a general front end. What we are focusing on in this course is the filter. So in other words, the filter in real life will never be driven by a source which is outside the chip. This is the chip boundary. Okay. What I want you to realize is that the actual filter, if found working, will be functional only in this kind of scenario where it is receiving its input from an amplifier which is already there on the chip, and 2, it is driving an A to D converter which is on the chip itself. So in principle, this filter will never see the outside world, right. It is always there only as an embedded part of a larger system, right. But unfortunately, when you need to test it, you can't really test the filter in situ like this, because you really do not know if something is wrong. You do not know whether what is wrong is the amplifier or the A to D converter. In principle, one could say I will put a sine wave at the input and then record the data at the output of the A to D converter, and from that we should be able to figure out the frequency response of the filter, right. Now that all sounds great the moment if everything is working, but if something is not working, you don't know, it's because the even if a filter is working and the A to D converter isn't, it's impossible to place the blame on anybody, right. So even though these individual building blocks may never see the external world, it is important to be able to test and characterize them, just to make sure that they do meet spec and they are not faulty, all right. And most signal chains today, as I have indicated repeatedly before, are fully differential, right. So the true signal is not either the voltage or current on this wire or this wire, but the difference between the two. So the filter will be fully differential, the A to D converter will also be fully differential, and so on. Okay, so that's the problem that we are trying to attack today. Figure out what one might do to be able to test the filter. The simplest thing one can do is what? What is the dumbest thing that you can think of? Okay, great. So we say, okay, I know that the filter is not going to, in practice is never going to talk to the external world, but I need to test the filter. So I'll say I will have these wires which will not be connected in the real system, but for test, let's say I bring it out, bring out these 4 wires as pads on the chip. Okay, so at least now I have access to the input and the output of the filter, right? And so what do you think is the problem with this approach? I mean, in principle, if I now want to find the frequency response, what should I do? I will put in a sine wave between these two terminals, measure the magnitude and phase of the sine wave coming out. Okay. So what do you think are the problems with this approach? Pardon? Okay. One objection is that, hey, now you're saying apply a sine wave between these two wires, right, or these two points, but the VGA is simultaneously also trying to drive the input of the filter. So what must one do? Either you have an enable signal. I mean, this unfortunately this is not digital, where you just have an enable signal and things all kind of I mean, enables that disable, which will automatically this thing. You have to make sure that the VGA is cut off from the filter physically, some way or the other. And one way of doing that is to put 2 switches there, right, in principle, right. Maybe there may be other problems with the switches that one way we may not be aware of at this point, but at least in principle it seems like putting switches between the variable gain amplifier and the filter is a reasonable way of going about it. Fine. Okay. So what other problems do you think?
There might be too many filters.
No, there's only one filter. Pardon? Okay, so then one might say, okay, what about the A to D converter? Okay, then I say I can put 2 switches and isolate. Whatever you can do with the VGA, you can do with the A to D converter also. So basically, in principle, we have cut off the connections between the filter and the VGA, as well as the output of the filter and the stage following the filter. Yes.
Sir, how can it be cut off, because that will change the loading of the filter?
Yeah, well, yeah. I mean, at this point, let's assume that the A to D converter load is 0.
Small pads might load them.
What is the problem with doing this? Now I will say put a sine wave, measure the output at the.
The pad connection will have their own band.
Okay, so the filters you have seen so far are what are called are all GMC filters, correct? So the last stage of the filter will be some character like this, and now you have these two wires being tapped off. You understand? This is the filter. That is the filter. Okay, and now you have these two wires which are being tapped off the. That is exactly what we are doing now. We are tapping the output of the filter. You understand? Okay, so what do you think are the problems?
We should put voltage buffer and then
That is the solution. What is the problem you are trying to solve?
let's say integrating capacitance.
So, okay, to give you an idea of why this is a problem, I mean this side of the crowd, do you think there is a problem or there is no problem?
Measurement equipment can also.
What about the measurement equipment?
That you also have an impedance.
Okay, so to get matters straight, let's get an idea of the physical size of all these things. You understand? Hey, we draw transistors so big, doesn't mean the real transistor is that big, right? So, okay, so these are all examples of real chips containing real filters. Okay, so some terminology first. I am sure all of you are aware of this, and so this is a PC board, right? I am sure all of you know this. Okay, this contraption here is an IC that you also seen, correct? So this is actually what is called the package. Okay, the actual IC is not the full thing. Oh, I meant to show you another picture. Okay, so before we see the package and the board, we should know what the chip is, right? The chip is that small squarish thing inside the. Vivin Thomas, can you see what is there? Where is the chip? Here, Vivin Thomas, no. Pravin Samuel, yes. The square, the greyish looking square inside the blue circle is the actual chip, right? It could, in principle, it consists of a million transistors, right? This chip is mounted in a package. So this stuff is one example of a package, right? This is what is called a dual inline package. This is the same thing that you are all familiar with in the lab. This is not the only kind of package. In fact, this is not a particularly good kind of package for high frequency work, but this is an example that you are all familiar with. Okay, and this cavity, as you can see, the chip is sitting in a cavity. You understand? So this is the lid of the cavity, which has been opened in order to take a picture, right? Otherwise, the chip would probably look like this, correct? This lid has been opened and the actual chip is inside, right? And these are all the pins of the package, correct? The pads on the chip have to be connected to pins on the package. So what is done is that this thing is stuck using glue. I mean, for all practical purposes, some kind of glue. Fancy terminal, some epoxy kind of stuff, right? We make sure that this chip doesn't move when the chip moves. The whole package moves, right? So for mechanical stability, you can't just leave the chip floating with wires hanging all over the place. The silicon die is actually pasted onto in the package cavity, right? Now these pins are also routed to the package cavity, right? Now all the job that needs to be done is to connect the pads on the pad openings on the die, right, to these points here. In fact, it is not very clear, I am sure, but I do not know if you can see these discrete type of marks. Those correspond to each one corresponds to one pin. You need to make a connection from this character to that thing. You understand? And that is called, how do you think you are going to do that? It can't be wireless, right? So there is going to there has to be a wire which connects the from the die to the package, right? This is usually a gold wire, okay, and this whole process is called wire bonding. Okay, there is an automatic machine which in a semiconductor line there will be a machine which this whole thing will be going on so quickly. There is a robot type thing which basically has memorized the locations of the pads, right, the locations of the corresponding points in the package, and there is something which rapidly goes from pad to package, pad to package, pad to package. I mean, cuts off the wire after the bond is made, and so on. All this happens very, very quickly. You understand? So, and obviously once you have the chip packaged, this is how it will look. Here the lid has been closed so that moisture and sambar and all this stuff doesn't get into the cavity, right, and then you put it on a board for characterization, right. So why do you need all these other extras to characterize the chip? We need various stuff like supply, right. You need bypass capacitance between supply voltage and ground. You also in your lab you probably have seen what happens to circuits when there is no decoupling of the supply, right. So for example, all these big electrolytic capacitors are examples of decoupling capacitors. Then you need perhaps you need a clock for a DSP. This only consists of a filter, so it does not require a clock. Some switches, let us say you want to set some bits to ones or zeros, there are some switches, these are examples of some switches you can set on the board, right. And signals are all on the, as I have discussed before, all these paths are differential paths. So the input signal going in must be a differential signal, and this must be riding over a common mode voltage, right. So, but unfortunately most test equipment you can buy today is single ended, right. So the actual sine wave that you get from a signal source is with reference to ground. You will not get two sine waves which are 180 degrees out of phase riding over a common mode. It is your job to take the single ended voltage and convert it into a differential one. So how will you convert from single ended to differential riding over a common mode? There are many ways of doing it. Single ended to differential conversion. What do you think you can do? You have some voltage source here which is reference to ground. I want VCM plus say A cos omega t and VCM minus A cos omega t. This is the stuff that must go into the chip. This is what I have available to me. How will I convert this to that? Pardon? What kind of inverter? Okay, so what is the cheapest way of you can think of doing this? I mean, one suggestion was that you have an amplifier with a gain of +1, you have an amplifier with a gain of -1, and then adjust the bias quiescent voltages of the outputs of the amplifier properly so that they are riding over the right bias voltage. That is fine. Unfortunately, at very high speeds that is problematic, because the gain of amplifier, the bandwidth of the amplifier with the gain of +1 and the bandwidth of the amplifier with gain -1 will not exactly be the same, which means that the phase of the amplifiers, both the amplifiers will not be exactly equal, which means that the two voltages will not be exactly 180 degrees out of phase. Okay. So that is one problem, but at low frequencies you can do that, and that is done quite often. But can you think of an even simpler thing without any active devices at all?
Battery and capacitors. So I can add a voltage source in series with the sine wave.
No, where is the voltage source?
The VCM, the battery of VCM, that will directly give me VCM plus A.
Yeah, sure. Okay. What about VCM minus A cos omega t?
So I can invert the battery so that I get A cos omega t minus VCM, and
Yes.
then finally I can invert that.
How do you invert that voltage?
Inverting is basically by a delay.
If you have a fixed, I mean, so one idea was, why don't you delay one? I mean, after all, minus A cos omega t is A cos omega t delayed by pi, right? So you can put a delay line and then get the inverse, is what somebody suggested, right? The problem with that is that as the frequency changes,
The delay will be
this pi radians has to change. So that's a very difficult thing, right? So what do you think? What else do you think you can do?
We can take two resistors, and in between the resistors we can put VCM, then one end will be VCM plus the divided resistor.
How will you get VCM plus you will get, but how about VCM minus?
We will take two resistors down the resistors.
Have you all heard of a transformer?
yes.
Yes. Okay. So now that you have heard of a transformer, how will you configure it to get so there is something called a center tap transformer. There is nothing great about it. You can take two transformers, if you do not know what a center tap transformer is, and then equivalently reverse the dot connection, right. So basically a center tap transformer is something where you have an access to this, the central tap. If the number of turns, all the turns are the same, then all that this induction law is saying is that the voltage between these 2 points is twice the voltage across the primary turns, correct. Okay. So it does not say anything about the absolute voltage either here or here. All that Faraday's law is saying is that the voltage across, induced across those two end turns, must be double the voltage across the primary coil. You understand? Okay. So now that we have established that the voltage across the secondary is twice the primary, if I simply connect this to VCM, then this voltage is going to be VCM plus A sin omega t, and this voltage is going to be VCM minus sin omega t, right. So this is a common trick used to convert a single ended voltage, which is what is available from test equipment, right, to a so called balanced output, where you can see that the two voltages can be thought of as the two arms of a balance, right, going about a average value. So this is nothing but VCM plus A cos omega t, VCM minus A cos omega t. This is what is called an unbalanced to balanced converter. Okay. All right. So we also need the opposite. Why? Because our circuit outputs are all differential. The measurement equipment can only react to single ended stuff. So we need to convert from balanced to unbalanced. So, that what would you call it? BAL to UN. So, often all these things are called balloons. Okay. Now, nothing to do with BALL OON or BALON, whatever, right. Okay. So, this term balloon is used interchangeably for both the unbal and the balun. Okay. All right. So, therefore, what we need are these transformers, also known as balloons, and so in this picture, for example, this is a transformer and this is also a transformer, this is also a transformer, right. This is this, I mean, it's the same transformer turned this way or that way becomes balloon or unbal. So, this is the balloon or this is the unbal, unbalanced to balanced, and this is the output of the filter, unbalanced to unbalanced, this goes to the test equipment. These are what are called connectors. Okay. And please note that the chip is very small, the package is larger, the board is even larger. So, by analogy or interpolation, the measurement equipment is going to be even larger. So, that's a big box like this, which costs more than all these other parts multiplied by 1000, right. Okay. So, the box which measures the frequency response, basically now all that you are doing is you have a 2-port network from here to here, right. It is nothing but a 2-port. You have one input port and one output port, right. And what you are interested in measuring is what, if you have a 2-port, what are the parameters that of interest in a 2-port? Any 2-port can be characterized by, in general, 4 parameters. So, there is a whole bunch of, I mean, you might want to you may like the Z parameters, you may like the H parameters, you may like the Y parameters, right. It turns out that for measurement work, right, people like what are called the scattering parameters or the S parameters. I mean, this is one more manipulation of voltage and current. I mean, at this point I will not get into the details of S parameters, but all I will say is that just like you can convert from Y to Z and Z to H and one set of parameters to another, you can also convert from Y to S, right. The scattering parameters are, again, you need only 4 of them, right, and the scattering parameters can be converted into Y or Z or H or G or A, B, C, D or your any other favorite parameter set, and and vice versa. Okay. For measurement work, it turns out that scattering parameters make a lot more sense than Y or Z or H parameters or G parameters, and the reason has to do with whenever you want to measure Y parameters of a box, what are you doing? So, whenever you are measuring Y parameters or Z parameters, you are either short circuiting or open circuiting some port. Okay. So, it turns out that at very high frequencies, if you have amplifiers with high gain and so on, this concept of open circuit and short circuit does not exist in practice. These are all only theoretical. So, every short circuit is actually can be modeled as an inductor, and every open circuit, I mean, beyond a certain frequency, no short circuit is true short circuit, and similarly beyond a certain frequency, no open circuit is really an open circuit, its impedance actually starts to fall. Okay. So, true short circuits and open circuits never exist in practice. So, it is impossible to enforce those conditions to measure the parameter matrices, right. So, it turns out that the S parameters are measured with resistive termination, often 50 ohms, right, and the measurement is also actually much simplified with S parameters, which is why they are used all the time. So, a box which takes a 2 port and measures the S parameters, right. I mean, for at this time you may even think of this as a box which measures Y parameters, because in principle the Y parameters can be gotten from the S parameters. Okay. So, what do you think it involves? What all do you think is involved in measuring the Y parameters of a box? Measurement of current and voltage, and what else? You need Y parameters as a function of frequency, and which parameter would you think would be 0 in a filter? Y12, I mean this is an active filter, right. So, it is not bilateral device. Since it is unilateral, all the reverse transmission parameters in principle must be 0, be it Y12, Z12, H12, G12, S12, all 1, 2 parameters must be 0. In other words, if you wiggle the output, nothing must happen to the input, that is what it means. You understand? So, and the frequency response, finally you should be able to extract from which parameter? From the Y21, you are interested in the Y21, you understand? Okay. So, now that we understand this, our measurement setup so far looks like this. This is the fully differential filter, this is our balloon, right. This is the unball, and this is the balloon. Okay. And this here I need to in principle put a voltmeter which can measure the magnitude and phase of the sine wave coming there. So, this is the measurement equipment. As I said, this box measures the S parameters of the 2 port, which are equivalent to, which can be translated into Y parameters and so on, right. And the box which measures the network parameters of a network is called, what do you think you could call it? A box which measures network parameters, come on, what would you call it? Forget what it is called. Network measurer, network characterizer, network analyzer. Okay, so it is called a network analyzer. Okay. All right. So, the network analyzer is a box which, I mean, we want to characterize this across frequency, correct. So, what do you think must vary? What the analyzer is doing is varying the sinusoid frequency, and for every frequency measuring the 4 parameters of the 2 port by measuring the voltage and current at the edges of the box. It is a box, right, it can only measure stuff at its entrance or exit, you understand. It does not know that your filter is 2 miles away, you know, connected to the box through cables. It is not as if, please note that this is the board. So, again it is not as if there is wireless communication between this and the network analyzer. You need to connect it with a I mean a wire is a very bad thing to say, it is a cable, right. Okay. And similarly there is a cable connecting the connector at the output to the network analyzer, you understand. So, the stuff that you actually want to test is some small thing inside, right, and now you have this huge setup, okay, which which you have to have, right. So the question now is, okay, now after connecting these cables and all this stuff, is my filter A still working, okay, and if it is working, is what I measure is it the inherent property of the filter, or has it been modified completely by all these extras hanging on to the filter? You understand the problem, okay. So even though all this is drawn to the, obviously the scale of this diagram is completely off. This is probably a fraction of a millimeter, and this is a fraction of a mile, so it's the scales are completely off. You understand, and the cables are not shown here. They will be, it's not uncommon to have a 3 feet or 1 meter long cable. You understand. So one thing with doing this directly with the filter is that now any impedance here, when reflected back, will be multiplied by some constant, isn't it? You have a transformer, the secondary impedance divided by primary impedance is square of the turns ratio, right. But basically the bottom line is that all this stuff, which is the long cable and the whatever input impedance that the network analyzer has, will all now load the filter, right. So if you had a GMC filter like this, and if you put some arbitrary impedance here, what do you think happens to the filter? Ideally you wanted to only have a capacitance. Now in parallel with the capacitance, there is some unknown impedance as far as you are concerned, correct, because there is a long cable and there is probably a lot of stray capacitances and all this stuff, and they completely screw up the filter. You understand. So what do you think you can, how do you think you can fix that problem? Voltage or current buffer, something that senses the you need something that senses the filter output without loading it, right, and then drives the external world, right. So an example of what is happening is in this picture shown by, for example, TB stands for test buffer, right. The test buffer senses the output of the filter, right. This is the chip boundary and goes and drives the balloons, okay. All right. So that is not good enough, because as I said, the network analyzer measures the parameters from here to the output of the test buffer here. You understand. So whatever you are measuring is this whole thing, which consists of the input cable, this transformer, any parasitics of this pad, the filter, the test buffer, this stuff, and this cable at the output. But what are you actually interested in? You are only interested in the filter response and not all the other stuff. So what do you think you can do?
Categorize each of the elements separately and then use transmission parameters.
Yeah, so basically you say somehow if I can get rid of the unwanted stuff, right. So I measure this response, right, but if I somehow got the response of the rest of the stuff without the filter, then in principle you can go and back calculate the response of the filter itself. So recognizing that the response of the filter is nothing but this voltage divided by this voltage, right, the output of the filter divided by the input of the filter, one can say if I had another identical test buffer which sends the input of the filter on the chip, right, and drove a similar balloon and we use the same cables and so on, then what is the gain of this path, of the direct path, or the path which does not go through the filter? It is the input path multiplied by the gain of test buffer 1 driving this impedance. This impedance by assumption is the same as the impedance here. So, if I measure the gain of this path, I will get G1, correct, of the direct path. If I measure the gain of the filter path, I will get G1 times filter response. So, by dividing these two responses, I should be able to get the gain of the filter response, the gain of the filter, irrespective of what how bad the rest of the setup is. The bandwidth of the filter and of the direct path, for example, there may be significant attenuation here because of bad cables, whatever. Similarly, there may be attenuation here, right. However, this is common to both the filter path and the direct path. So, taking the ratio of the two, we should be able to remove the effects of everything and actually get the gain of the filter itself. Does it make sense? So, this is what is usually done. So,
how do you ensure that the impedances are same?
Pardon?
How do you know that the impedances are same?
It is the same cable. So, I will remove this the connection from. So, for example, here, right. So, this path is common to both paths. This is the input paths, right. Then this is the one is the direct path and one is the path through the filter, right. And you can see that this is a copy and paste of this, right. So, in an attempt to keep this exactly the same as this, all I will do when I am measuring is remove the cable from this connector and put it there. So, it is the same cable, it is the same network analyzer, everything is the same. Does it make sense? Okay. All right. Now that, so in other words, there are two paths. One is the path is the direct path, and the other is the filter path. And by taking the ratio of the direct path output to the filter path output, we should be able to get the filter response. So, that is basically.
Why is that two test buffers? You can just bypass the filter for direct path.
You could you could so one this thing is that hey, why not just connect, why don't you have a switch which directly bypasses the filter. Often it if you can do that carefully, that is okay, but otherwise what happens is that if you directly connect switches here, because the way you connected the filter, it is if you do not do it properly, what will happen is that the impedance at this point will change for both the measurements, right. So, you want the rest whether you connect whether you are measuring the direct path or the filter path, you want this voltage to remain the same. So, as long as you can maintain that, if you can bypass the filter properly, that is fine. Another thing that we have also done is, instead of having two different paths, we can mux these two into the same pads. You can either keep, electronically turn this off and keep this on, or vice versa. So, this becomes just the same, absolutely the same path without any mismatch. Okay. So, now that that is done, the math is fairly straightforward, right. Let us say the transfer function from Vi to the input of the filter is Hin, the transfer function from the input of the test buffer to this output is Hb, right. The direct path output is Hin times Hb, the filter path output is Hin times Hf times Hb. So, you measure this as a function of frequency, you measure this path gain as a function of frequency, take the ratio and you are all set.
We are assuming test buffer is working properly.
Pardon? Here we are assuming that everything is working properly.
It's like, sir, we are testing the filter.
Yes.
So for that we are making another equipment. Sorry, another.
Yeah.
So finally something we should have a reliable.
No, nothing is reliable. As long as both of them are running equally unreliable, that's fine. Right? As long as this and this are the same, right? These two will get cancelled. You understand? Of course, if this gain is 0, then you're finished. You understand? Okay. I mean, when I say these test buffer TB1 and TB2 doesn't matter, it doesn't mean you can remove them and then the whole thing will work. You understand? All that I am saying is, if this have a bad response, for example, a frequency response whose bandwidth is say even lower than that of the filter, right? The actual voltage you measure here may be very bad, but that will be there here also. When you take the ratio, that will go away. You understand? Okay. Now, so you take the ratio of the two and you get HF being the ratio of the filter path to the direct path. Quite straightforward. Okay. Now, so in principle, it seems as if everything is fine, and however bad the test buffers are, or however bad the package is, for example, right? The filter gain must be, we should be able to measure the filter gain accurately. Unfortunately, that's not what happens. So this is examples from a real filter. It's a fifth order Chebyshev filter. As you can see, the magnitude response is plotted on the y-axis in dB, and the response which is going all the way to minus 100 dB at 500 megahertz. The x-axis is in megahertz, right? So this is a fifth order Chebyshev ladder filter. The ideal response is supposed to be to go up to minus 100 dB gain. Minus 100 dB gain is 1 part in 10 power 5, right? Okay. And you can see that when we actually measure the filter, up to here we seem to be getting, I mean, this is the ideal thing that I was shooting for. Now when I measure up to about 40-50 dB, that's up to 150-200 megahertz, the response seems to be following the ideal characteristic. Beyond that, it seems to be deviating. Now there are two possibilities. What are the possibilities? Of course, the one could say, hey, the measurement equipment is bad, and then that's just like you guys say, oh, the oscilloscope is not working, right? But the network analyzers are extremely expensive boxes, and after paying $300,000 for a high-end network analyzer, you really don't want to be saying the network analyzer is not working. You understand, right? So what are all the possibilities? Filter may not be working. I mean, you design the filter, so you are all, I mean, right? So you're not very happy saying, my filter is not working. So what must therefore not be working? Well, there's something happening, right? My filter is good. I think the test equipment, of course, by definition is good, right? There must be, I mean, all this, but all these extras are there around the filter, right? So it's likely that they are screwing up stuff, and see, my design is working quite well because in the passband things seem to be quite good, right? And all the way up to 50-60 dB, it's following the ideal. Now it's kind of, even if I wanted to make something like this, it's probably very difficult, right? So it also turns out that the moment I change the package, when I say change the package, it doesn't take very much. So when I say one second, let me see if I have. So this is a picture of the chip within the cavity, right? And now I hope you can see some wires connecting to this. So these are the bond wires. So this is the actual filter chip. I don't seem to have okay. So because of all these extras, it seems like there's something happening, most likely the measurement technique, right? So there's some inaccuracy here. So it turns out the reason for that is that please note, as I said, this IC is mounted in a package, right? So there are actually inductors going from the pads on the filter to the pads on the from the silicon die to the package there are these inductors flying in, correct, and you have which are basically many wires going, gold wires going from point A to point B, all these wires are parallel to each other. So at high frequencies what is happening? I mean there is coupling. I mean when you have two conductors at high frequencies they will talk to each other, right. So they will all talk to each other. So at very high frequencies what is happening is, even if my filter works very well, in other words if my filter is working very well at very high frequency, what is the output here? It's close to 0, right. So in principle this must be 0, right, but in practice what is happening? Everybody is talking to everybody else, you understand, okay, alright. So what you are actually measuring here is not the stuff coming out like this, but stuff coming through various coupling paths between various wires, because everybody is talking to everybody else. Does that make sense? Okay, so to see the magnitude of the problem, you take the same PC board and you remove the chip, right. So now there is no filter path, there is no buffer path, there is nothing, correct. So these are 3 isolated ports. So in principle if I put in a high frequency sine wave here, I should get any parameter I measure, either y21, y12, all must be 0 because there is no coupling at all between these 3 ports, and when you actually make a measurement this is what you find, okay. You can see that up to over 300 megahertz this response y21 or y12 or S21 is like minus 100 dB, okay, which happens to be the limit of the resolution of the measurement equipment. But beyond 300 megahertz you can see that what is supposed to be very very small is ideally supposed to be 0 starts to go up with frequency. You understand? The moment I put in the chip, but I put in the package, but there is no chip inside, right. I can always take a dummy package and put it in and see what happens, what the package is doing to the isolation, and you can see that the moment I have a package, the isolation between 2 ports, which is ideally supposed to be infinite dB, minus infinity dB, is actually going up with frequency. That makes sense because induced currents all are proportional to frequency, correct. Now for example at 400 megahertz the isolation of the board is only, of the package is only about minus 65 dB. In other words, if you took 2 pins, another 2 pins on the package, they were not connected intentionally, right, just through RF coupling at 400 megahertz, if you put in a volt here you will pick up a millivolt there. You understand? I mean this is not to be seen as something bad. I mean this is why your cell phones are working. You understand? If this wasn't there, then I mean there is no physical connection between your phone and the base station. How is your cell phone picking up signals? It is all because of traveling waves and all this stuff, right. But this is a manifestation of the same phenomenon. Okay. So this is, I mean one might say a factor of 60 dB is it's like 1 part in 1000. This is a very small number, right. So what is the problem with that argument? The stop band ejection of the filter at 400 megahertz is 90 dB, right. So clearly one cannot measure a filter with a stop band attenuation greater than, I mean so unless the filter transmission is much greater than this, you will be swamped by this feed through from happening in the package. Does it make sense? So basically all this measurement is telling you that at 500 megahertz in this particular example, I cannot measure a filter whose attenuation is, I mean more than 60 dB, of course, even unless the attenuation of the filter is much less than in magnitude less than about 40 or 50 dB, right. You understand? So which is why you see that the accuracy of measurement in the pass band is quite good. In the stop band, we saw that I mean what, therefore you are measuring here is not the response of the filter, but stuff, you know, everybody is talking to everybody, and okay, you understand? Okay. Now it also makes sense that when you change the package, the response changes, right? If the filter was truly at fault, then if the package changes, nothing should change, right? You should see the same response in both cases. Does it make sense? Okay. So what do you think you can do to fix the problem? So okay, let's do some analysis and see what the real problem is. So in other words, ideally this is the signal flow graph that you wanted, right? Hn, Hf, Hb, Hn and Hb only, correct? But now every node is talking to every other node through these coefficients k1, k2, and this is the real signal flow graph that you actually have, correct? So the gain of the direct path or the gain of the filter path, for example, is Hn. You can write Mason's rule and all this stuff, but intuitively you can see that there will be one component Hn, Hf, Hb. There will also be k1 times Hn, correct? There will be k2 times, there will be k3 times Hn, Hb times k3, right, plus k2 times, I mean there is also stuff which Hn, Hf, Hb comes back, right, goes through here for example and then comes there, right. So I mean this is nothing but Mason's rule, you just write the stuff out and then you will get it. So which do you think will be, I mean k1, k2, k3 etc. will all be very small, and in the stop band Hf will be also very small, right. So you can do the math and you will find that the dominant components here, right, at very high frequencies are basically Hn, Hf, Hb plus k1 times Hn, right, that is basically Hn and then k1, and k3 times Hn, Hb times k3, okay. All the other terms you can, you know, convince yourself that they will be very, very small. So in other words, in the stop, in the pass band you have no trouble because these guys are very small compared to Hn, Hf, Hb, you understand. But in the stop band this is very small compared to k1 Hn and k3 Hn, Hb. So what you are actually measuring is some are these are k1 Hn plus k3 Hn, Hb. That is why you are seeing the rejection being so bad in the stop band. So the idea is to say, if I switch the gain of Hf, if I multiply the gain of Hf by -1, what do you think will happen? You understand? In the filter stop band, right, this path is not contributing anything, correct. What is actually coming is just direct feed through. So now if I now multiply this by -1, what do you think will happen here? There will not be much change, right. So but however, if you subtract the two measurements, one with Hf and one with minus Hf, what do you think will happen? Yeah, you will get. So the key to fixing the problem is to understand that the feed through terms do not depend on Hf at all, correct. So if I make two measurements, one with Hf being equal to 1 and one where Hf is multiplied by -1, and multiplying by -1 is extremely easy, right. Why is it very easy? How do you make HF equal to minus HF? I mean, one idea is to say put an inverter, right? It's not needed because you have fully differential stuff. So all that you need to have is switches which which basically cross couple the input and the output, right? So so the idea is to measure the filter path output with the sign of HF changed, which is very easy to implement, and therefore the signal due to the filter is inverted and the feed through remains the same. When you subtract the two off, the feed through goes away, right, and you get H in, HF, HB. Similarly, you will get the direct path also will have the same problem. So you can do that to both of them, and so you do all the math, and finally if you subtract with +1 and -1, you get H in, HF, HB times 2. Direct path also is you will get 2 H in HB. If you take the ratio of the two, then you should get simply HF, right.
So direct path, how do you get it? There is no HF.
No, there is direct path also. For the direct path, HF is 1, that is all, right, that is the only difference. Okay, so now let us see what happens when
That is inside the chip, like HF, both the systems.
all that is inside the chip.
So how can we swap?
Yeah, I will show you, right. So to test this idea, one of my PhD students built a chip, a GMC filter which is programmable from 70 megahertz to 5th order Chebyshev filter, the band edge programmable from 70 to 500 megahertz, okay, in a 0.35 micrometer CMOS process, which is 4 times slower than the process in which you are working. You are all working in a 0.18 micron CMOS process, right, a fixed GM bias circuit to stabilize bandwidth and so on. So the question is, how will you invert the gain? How will you multiply the gain of the filter by -1? And that is quite straightforward to do, because all that you need to do is, if you want the filter gain to be +1, you connect these switches this way. If you want the gain to be -1, you cross couple these switches. These can be CMOS switches, right, very easy to implement. You have a control signal, logic signal here, which either puts the signal this way or flips the polarity of the switches. So for example, if you want to measure the filter gain with filter gain being equal to +1, this is how it will look like. Filter gain equal to -1, that is how it will look like, right. And this is a test buffer. This is nothing but a voltage controlled current source, okay. All of you said voltage controlled voltage source. It does not matter, as long as it is voltage controlled, whether it is a current source or a voltage source, it does not matter. It turns out it is much easier to implement a current source than a voltage source. This is nothing but these are the switches, correct, which are controlled by a logic signal. This is a what kind of amplifier? Common drain. So this is a voltage controlled voltage source, right. Then this is a what kind of contraption is this? It is a differential pair with a cascode, okay, and these go to the bond pads. The load resistor is actually the resistance of the measurement equipment, okay, some impedance of the measurement equipment. So this is the photograph of the chip, okay. So this is the filter. This is one is the filter path, one is the direct path. This is the current distribution fixed GM bias, okay. These are all the pads, and you can see that these are all actually the gold wires which are gone, and these are the pad openings, okay. As I said, we need to connect these to the package with bond wires, right. These are the ends of the bond wires. So you can see that they are actually going up. That is why this part is in focus and this part is not in focus. Is that clear or no? Shravan, Siddharth? No. If you, I mean, this is the hole here, man, and there is a gold wire which is supposed to connect here and then to here. This wire will not be planar with the IC, so it will jump up like this and then come like this, correct. So, if you take a picture with focusing on the at this level, it will follow that things which are not in the focal plane will be out of focus. So, that is why you see here stuff is out of focus and stuff here is in focus. Is that clear? Okay. And this is the as I showed you earlier, the dye within the package cavity. So, once you do this, you can see that these were the two curves that we saw earlier, right. So, once you do this positive, negative, subtract and do the ratio, you can see that the filter response actually follows the stuff to up to 400 megahertz, for example. You can see this is actually following the ideal all the way up to here, right. Therefore, leading you to the conclusion that the filter is working, right. Of course, beyond 450 megahertz or so, you see that the stuff already also starts to rise again, and that is because of the various approximations we made in the whole technique. But this is something which earlier, I mean, extends the accuracy of measurement by almost a factor of 2 in frequency and about 3 orders of magnitude in magnitude. Earlier you were able to measure only stuff up to 40-50 dB accurately, right. Now you are able to measure stuff up to 80 to 100 dB and over a much wider frequency range. You understand? So, and of course, in the pass band, this is a fifth order Chebyshev filter. So, you can see that it is indeed 1 dB ripple and all this. So, so this is what I would call state of the art in accurate measurement of on chip active filters, right. And yeah, so I will stop with that. We will continue in the next class.